All right, we ended last week with the discussion. I think is it 15%?
Yeah.
So the 15% rule state that changes in KV by 15% cost are double in radiographic density. So a small change in KV causes a huge change in radiographic density. Whereas in mass, you need at least double the mass to double the radiographic density. In terms of intensity radiation exposure, the same thing applies. A small change in KV will have a huge change in exposure factor, radiographic intensity. 10% increase in KV will have a huge increase in intensity, whereas a 10% increase in mass will only cause a small amount of change in intensity as well. To calculate changes in KV in relationship to changes in intensity, we use this equation. The original intensity, I1, over new intensity, I2, equals original KV squared over new KV squared. That's to get how much of a change in KV in relationship to intensity. So let's do an example. This is from the book. A certain technique calls for 110 kV using 10 mass, which result in an extra intensity of 0.32 milligram air current in air. If the kV is increased to 125, what would be the new extra intensity be based on this change? Using our equation, I1 over I2, KVP1 squared, KVP2 squared. Okay, comparing the missing elements. Original intensity is given as 32.32 gray. When KV is set at 110. We want to know what is the new intensity when KV is increased to 125. We could actually do this by using factor of 5, correct? So this would be 22, and this would be 22 squared, 484, plus multiply, x. 25 squared, it would be 625. 625 times 0.32, 200. Divide both sides by 484. So the new intensity will be 0.41. So it changes the KV from 110 to 125 causes a change up by from 0.32 to 0.41 milligram. So this is how you get the relationship between change in KV and intensity. Any questions? Pretty straightforward. Questions, concerns?
I have a question. GYA, doesn't that stand for
Air.
air?
Yeah. So really great. That's how the first you never discussed about how Lincoln calls measured in gray, like gray in air, or gray in tissue. Ed Kermer. And of course, distance also affect exposure and intensity. We discussed about inverse square law, how changes in distance can either increases or decreases exposure by a factor of where the distance is by square. If you decrease distance by half, then your exposure factor will increase by factor 4. If you increase the distance from 1 to 2, then you decrease your exposure factor by a factor of 4. So it goes by the square. When you want to figure out how much you need to change mass based on change in distance to get the same radiographic density on the radiograph, we use the direct square law. Because when we change distance, we also affect how it affects on the radiograph. Increase in distance will cause further penetration, so which makes the density decreases. To increase density with the same level over radiograph, then we have to change mass by a certain amount to have the same picture as it was before the change.
Density and then, okay, so then you said density and intensity, are they used inversely then?
No, to maintain the same radiograph density, then we use the direct square law.
Oh,
Density is referring to like the darkness of the film.
okay.
Because the further you are, the weaker it gets. So the weaker it gets, it's less dense exposure. So you have to change the mass to make sure they have the same radiographic density on the radiograph. We talked about inverse square law. You should all know these equations from by heart now, because this is chapter unit 2, right? And then we take 146. We talk about this a lot. So we could talk about direct square law. This is how we figured out how much of a mass changes to get the same radiographic density when distance changes. Original mass over new mass equals original distance square over new distance square. So it's a direct relationship. That's why it's called direct square law. Everybody have this? No? All right, let's do an example. Let's say if the original setting is as follows: 25 mass, 50 kV, with a distance of 40 inches. We use to properly expose a radiograph. That's the right amount of density that you want. But SID, which is source to image distance, just a fancy way of saying distance, is changed from 40 inches to 32 inches. What would the new exposure factor be to maintain the same density, assuming everything's constant? Using our equation, and here's 1, here's 2. 1 square, 2 square. Our original mass is 25. When distance is 4 inches square. We want to know what the new mass needed to use when distance is changed from 40 to 32 inches. Distance has decreased. So when you decrease distance, there'll be more penetration. Therefore, the radiograph will get, the density will get more darker. But we want to then have the same proper density. Based on this, what would happen to mass? Would it increase or decrease?
Decrease.
Mass will decrease to maintain the same radiograph density. We can actually reduce that by using factor of 8. Right? So this will be 5 and this will be 4. 5 squared is 25, 25 plus multiply x, it will be 25x. 4 squared, 16, 16 times 25. 400.
Bless you.
Yeah.
Divide both sides by 25. So, finally, yes, will be 16x. Our distance of 32 inches, mass will be 60. So our new answer, technique answer will be 50 kg at 16 mass, and distance is 32 inches. Also means everything is constant. Make sense? Any questions? I think that's the last equation. Yay. Okay, let's talk about filtration and exposure. Now we'll talk about quantity. The primary factor of that quantity is mass. And we've been talking about secondary, which is kV, distance, and now filtrations. Well, all I have to say about filtration in this section is that by adding more filtration, it will reduce patient exposure. That's the primary function of filtration, because it filters out all the low-level X-ray energy. Otherwise, the patient will just absorb them. So the purpose of filtration is to get rid of all the beam that's not useful in diagnostic X-ray before it interacts with the patient. So therefore, patient exposure decreases. Okay, X-ray quality. The quality of the X-ray beam pretty much means the penetration power of the beam, the strength of the beam. We're going to talk about the quality of the X-ray. Factor that's influence quality would be kVp, kilovolt of potential, substance here is kV, and filtration. Related to filtration would be the half-value lag, HVL. We're going to talk about this in a bit. Now, the quality of beam is strength, the strength of the beam. When it interacts with the X-ray film, the beam then produces radiographic contrast. And so kV pretty much control radiographic contrast of the X-ray images. So kV, that's one factor. It is the primary controlling factor in quality of X-ray. Therefore, it's also the primary controlling factor in radiographic contrast of the image. Contrast here, meaning it's the differences in terms of black and white on an X-ray film between two adjacent images. So you can tell the difference, the different parts. When we refer to an image that has high contrast, it's meaning you see mainly black and white, a distinct black and white. High contrast is influenced by low kV setting, based on also the anatomy it's looking at. So low kV produce high contrast. It's an inverse relationship.
Is it low KV?
Low kV gives
Makes
you high
sense.
contrast. Because there's less penetration. There's less penetration, so when looking at the radiograph, it's mainly black and white. And also depending on the anatomy. Low contrast, meaning there's more shades of gray on the images. When you see an X-ray film, you see not just a distinct black and white, it's a shades of gray. It's just more gray on the film. Low contrast is used generated by high KV. More penetration going into interactive film produces more of a contrast, so it gives you more shades of gray. So this is an inverse relationship between KV and contrast. High KV give you low contrast, low KV give you high contrast. High contrast means more black and white, low contrast just means there's more shades of gray in the X-ray film.
I have a question. On the previous slide, it said half value layer. Do we need to know what that is?
We're going to talk about that, so, because that's under filtration. So we're now talking about KV first. And KV is the primary factor controlling the quality of the beam, which also then primary factor controlling the radiographic contrast. Any other questions? Yeah.
So it's high KV, low contrast?
High KV,
No,
Okay, thank you.
low KV, high contrast. Only because there's less penetration, less interaction.
Is that a chicken wing on the next slide?
I'm sorry?
Is that a chicken wing on the next slide?
I think it's a doggy.
What?
The what?
A doggy? A puppy?
Yeah.
It looks like
I
a
got
chicken
from a
wing.
Van Ram somewhere. Anyway.
Where do you get a dog?
Huh?
He said dog. It's the wing of the
It
bird.
could be, I don't know.
It looks like a chicken wing.
I just got this, a good contrast image.
I've eaten a lot of chicken wings, I know. No,
That's a human too.
Alright, so here is an example of different contrast. So, low contrast gives you more shades of gray in the overall images of the picture. So another way of saying low contrast is that we have wide latitude. I mean, there's multiple shades of gray within that span. As the technology is wide latitude, means more room for error when you have when talking about technique. This is due to high KV. And on this side, I give you high contrast, a distinct black and white on the images. So it's just a narrow line of mainly just black or white, or just a close band. So we call it narrow latitude. There's not a lot of shades of gray. It's mainly black and white, like the band's more close related. And of course, contrast is also perception as well. What could be high contrast to you could be low contrast to other. And sometimes you work with some doctors don't like your images, and he or she think that the image could be too low of a contrast when you think it's perfect, and then you have to shoot it again or something.
I was gonna ask that, what would differentiate what you?
Yeah, so it's also a perception as well. Okay, but you can clearly see the difference between high and low contrast. But sometimes get too narrow of a band, like you're hot, so it's also a perception.
The higher contrast would show the, like in this case, if a bone was broken, it would show like the bone breakage a little bit.
For high contrast, maybe we look at like extremity, the one with a more clear detail. Low contrast, more like for abdomen. Yeah.
High contrast is low
Isn't
KV.
low KV problematic though, because you're absorbing more of the,
Yeah, I mean, low KV, it's also depending on the anatomy too, where you want to put, for hand, it's gonna be low KV. For an abdomen, you want high KV, based on the penetration ability of the beam, where you want it. For the abdomen, it's much thicker, so what you want, you need high KV in order to penetrate through. You don't want high KV on hand, otherwise just probably go through. Any other questions?
now
That makes sense.
Okay. All right, so here's our overall thing. In general, high KV gives you high quality X-ray beam. And then the opposite, okay, low KV gives you low quality X-ray beam. High KV will give you high quality beam, which means high energy, right? High energy meaning exposure rate increases, because KV is pretty much energy. High energy meaning what's the frequency?
High.
High frequency, right? Remember? High frequency, energy up, frequencies up, wavelength
Down.
down. High energy will give you high penetration power, more allow the X-ray to go through. More going through, more interaction with the film will give you lower contrast, more shades of gray. Of course, with more interaction with the film and after it go through, it will also give you more scatter radiation when after it's interact. So high KV will also give you more scatter radiation. That's pretty much sums it up, but here it is. Okay, secondary factor affect the quality beam will also be filtration. So filtration is secondary for both quality and quantity, correct? As I mentioned earlier, the main purpose of filtration is to reduce patient exposure. Since I kept mentioning that, most likely on the test, right? By adding filter to the beam, you are actually increasing the quality of the beam. Remember how I mentioned filter just knocked out all the low level energy, so quantity decreases, quality increases. Example I could make up with filter. For example, you have a 10 kV 10 kV setting, and since X-ray is quite energetic, how many is coming out? 1, 3, or 0, 3, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On an average, then you have to add this up, and this is just a demonstration of how filter works. So let's add up all the kV. 1 plus 2 plus 3 plus 4 plus 5. Give me 55. And 55, to get the average, 55 divided by
3 or 10.
10. So 11 kV on average, right? If you place a filter in and it going to absorb the low level energy, let's say you place a filter that absorbs all the low level energy up to 5 kV. So let's go. So this, and all you have is this. So we add up the average. 6 plus 7 plus 8 plus 9 plus 10, 40, divided by
5,
5. Give you,
8. Or is it?
no, wait, is that not 40, right? Did I add it correctly? No, I added somewhere. What? This one. Give me this, give me 5.5.
Like the 55
Divided by 10, give me 5.5, right?
Mm-hmm.
I want to catch that.
She did, but she's too shy to say. So.
Okay, all right. So the average is 5.5 kV. I'm like, how's that possible? Wait a minute, this makes no sense. And then, so as you can see with that filter, it's moving out all the low X-ray, so the quantity
It's going down.
decreases, but the quality
Increases.
increases. That make sense?
Mm-hmm.
Yeah.
I have a question. How did you get the 40?
40.
Because you added up from
Yeah,
6 to 10.
6, 7, 8, 9, 10.
Or
Remember the
the
average?
second half?
Yeah, remember the
Yeah.
average? Because it's filtering out all the low kV.
How do you
And
know
that's
where
just
to
an
stop?
example of how filters work.
Okay, but how do you know where to stop, like in this case?
I'm saying, it's just an example, whatever the filter is, based on the aluminum size, it will.
Oh, I don't, okay.
Yeah.
Is that moving the test? Do that math?
No, just give me an average word, as a minute.
It's not moving.
I can't tell you what's, I don't know.
You do know, you just don't. This one has up, it's up.
Nothing complicated.
So you say. Don't tell us that.
All right, related to filtration is a half value layer, which is it's a filter. This type of filter determine like how, you have to figure out how much of the thickness of the aluminum equivalent. Filter is made of aluminum, or aluminum equivalent. We measure filter based on aluminum equivalent. So half layer is determine the thickness of absorbing of the material that's necessary to reduce the X-ray intensity by half the original value. That's why I half layer. And it's just not a term for a filter. Increasing half layer means more thickness, quality increases. It's the same. Now I'm just going to go into the test you got how to get half layer.
So it's made out of aluminum, the filter?
Aluminum equivalent. So it doesn't have to be made out of aluminum, but when we measure the thickness of the layer of it, we measure it based on aluminum equivalent.
The example that you have, can we do that, like 1/3 of it minus out the whole thing, so you get the answer?
For that, like that, I mean, like damage, like it's 1/3.
Yeah.
So based on assuming everything is constant, when we're not factoring anything, it's just based on that. And as mentioned, how X-ray is 1/3 original value, so
Yeah.
we're not we just count this just to filter itself. There's a lot of things that works with it that makes the X-ray energy increase and decrease after the filter as well. So you're just assuming that just filter here on its own. All right, talk about this in 146 as well. There's different type of filters. So this is where there's cross blend here. That's made, that are part of the X-ray. Filtrations, by the construction of the tube itself, have inherent filters. So we call it inherent filtrations, based on the tube's construction. This inherent filtrations is about 0.5 millimeter aluminum equivalent. But by regulations, it has to have the filter of at least 2.5 coming up from the tube. That's a minimum by regulations. So we have to add extra material to make it up to 2.5. So there's other stuff in here, add filter and other factors such as the mirror that's inside there. What's the word?
Collimator?
Collimator, thank you, collimator. To give you about 2.0 millimeter aluminum equivalent. So for a total of 2.5 millimeter aluminum equivalent. So that's the minimum by regulation. We have by adding inherent and total. And there's different type of filters that we could use, and honestly, I haven't used a filter in years. it's
All computerized?
It's all computerized. It's very noticeable in traditional film, but we have what called compensating filter. Compensating filter is there's different thickness of the filter based on what anatomy you're shooting. The two most common type of compensating filter are known as the wedge and the trough. What is it called? Trough? The wedge filter, so this is an image of the wedge. This is quite often. We have a wedge and a trough. It's like a little book. It's like a book. With the wedge filter, well, this is valid wedge. This is made out of plastic, so it's put on the beam and collimated so it won't cover the light coming out. And it's filter, and honestly, I've never used it. So with the wedge filter, the way how it's set up, you place the thick part of the wedge on the thin part of the anatomy, and you place a thin part of the wedge on the thick part of the anatomy. When you make a radiograph, it will give you a nice uniform X-ray. Otherwise, with the thick part, what happened to most of the energy?
It's absorbed.
Yeah, and with the thin part, you go through. So the wedge help compensate so they look more even on a radiograph. That's all. So that one. And example trough. The main use for X-ray. The thicker part is mainly at the chest and the thin part at the spinal column. To help give a nice radiograph image. And have you ever noticed that a lot of pictures have a mustache? Because the author has a weird mustache. Sorry, what's that? There, yeah. Yeah, it was an author, he had this weird, funny.
Bouchon, right?
1800, yeah, Bouchon, 1800 mash death, like a creepy, sinister kind
That just looks like a shadow.
of. Huh?
It looks like a shadow.
Oh, is that it? Oh, yeah, 'cause that's his smash dash.
Mustache.
Yeah, his dash. Okay, extra interaction with matter. All right, so here we're gonna go talk about, back to subatomic particle again, so everything